Hello, everyone. We're gonna do set timer for 55 minutes. We're gonna do some physics. So here's physics 1112. We last left off with example 22.4. Let me go to that in the book. So 22.4, that's on magnetic force in a current carrying conductor. So we found out what that course is. And the forces, what we found is forgive me for a second. I want to write down what we're actually going to be doing. We're going to be doing section 22.8 all the way through to 23.3. So we're gonna cover a few things. Okay, so what we found is that the force is equal to the length times the current times the B field times the sine of theta. And typically that sine of theta is between the length and the B field. I'm sorry. No, it's the current direction and the B field. So theta is angle between current and B field. Okay, so that's what we did last time. So if you don't remember that, go back a little bit. Okay, so what we're doing now is torque on a current loop. So it's not super easy to see or draw. So one of the best figures to see this, and you know what? I don't like writing torque because torque has this symbol. I use that as my, wow, I am on fire. I use that symbol for the capitalization of torque. And we're going to look at torque from a current loop. But the current loop is in a magnetic field. Okay, so here we go. We have a magnetic field. And a good drawing of this is figure 2234, 22.34. Okay, so we have this magnetic field, and then we're putting a current loop into the magnetic field. Okay? And we're going to shoot our current in one side and out the other. So it'll be going up there, down there. And don't forget, this is our B field here. Okay. So that's kind of a sideways view. If we were to pretend that this was the center, then we would call this distance r. So can I make it equal? So it'll rotate about this radius if this is our axis of rotation. All right. We're also labeling this distance our width, W. So we've got this distance as our length, L. And then, of course, the area inside is our length times our width. All right. And then, of course, the width is equal to 2r. Okay, so that's our area. All right, now that's a sideways view. And then, of course, a top-down view would look like this. The B field is still going to the right, but we're looking top-down now. So here is our loop right in the middle. This is the width of the loop. And I'm going to erase these guys. What direction is the current going? It's going this way, right? It's going this way. So this is top-down view of our loop. And then it's going to rotate from the top down. It's going to rotate in some direction. It'll either rotate this way with an omega that way, or it'll rotate that way with an omega that way. We'll see here in a minute which way it's going to go. But let's talk a little bit about the equations of torque. So if you guys remember last semester, torque is equal to the radius times the force. So if you're spinning around this axis, right down the middle, your radius, if you were to apply a force, let's say we apply a force into the page at this point, okay, or all along this wire. That force is this force. Our radius is that radius here. And if we multiply by the sine of theta, where theta is equal to the angle between F and R. And it turns out that that angle, obviously, here's our force is pointing this way. If we look at the top-down view, our force is going this way. So that angle, of course, is 90 degrees for our situation. And sine of 90 degrees is 1. So we can just equate that to 1. And we get our torque is equal to R cross F. And we also noted up here that our width is equal to 2R. Or R is equal to our width divided by 2. So we can say our width divided by 2 So we have one force on the right side going that way. We have another force on the left side going down. And our torque is about this center. So our torque is actually 2 times F right and F left because they're equal. So F right is equal to F left. So we're going to have 2 times R times F, where F is equal to the magnitude of F is equal to the force left is equal to the force of right magnitudes. So that's where we're at, which means that the width times the force is equal to our torque. Now, what is the force? Well, what did we say earlier? Our force is equal to this and the sine theta, but we've already said that the sine theta is equal to 1. So ILB is our force. So here we go. Our torque is now equal to our width times I times L times B. And then in general, this is our case, but in general, this is the general equation. The width times the length times I times B times the sine of theta between I and B. Theta is the angle between I and B. Okay. All right. So, nice. So this is the general equation, and then we apply that general equation to our situations. We're going to continue with this same situation. And if we add many loops, so we have this thing come up and it comes over and we loop it around many times, and then we drop it down and we give it an axis that it can spin on. Then we've got this many loops situation. How many loops are there? There are n loops. So we have n loops. Then that means that our torque is equal to n. Real quick, the area on the inside is key. So let's just break this down for a second. Our width down here in blue. Ooh. Down here in blue. Our width times length is the area. Okay, so really what we have here is that torque is equal to our area times our current times our B field times the sine of theta between the normal of the area. So theta is really between theta is the normal, so that's how you do normal. The normal to the area and the B field. It's the angle between them. I didn't do that right. Okay, is the angle between the normal to the area and the B field. Okay, so that's where theta comes in, and this equation then is equivalent. So since that's equivalent, we can delete this, and we'll just put in our area. Okay, so the number of loops times the area, and in this situation, we would have a radius, so our area would be equal to pi r squared. Area times the current times the B field times the sine of theta. And so then as that loop, let's do a top-down view. So here's a bunch of loops right here in this angle. If we have our B field cutting across like this, the normal to the loops is perpendicular, so that's perpendicular to the loops, and the area of the loop, so that vector is A perp. And so our A perpendicular then has an angle, you can see it here, of theta, okay? That angle theta, if we drew this a little bit further, that's theta. And that's our angle between them. However, that angle is negative, right? Because we're pointing in two different directions, it doesn't matter. The sign of it is still going to be positive, and so that's all that matters. Okay. So we have this thing that spins around. We need to talk about the brushes. So how do we do this actually mechanically? So now look at figure 22.36. So there's this thing that spins around. So we want to have the current go this direction only, okay? So in order to do that, we hook up a current that comes in this way and goes out that way. And then as this thing rotates about its axis, it has brushes that connect to this side. So there's these little brushes. And then they connect to that side. And then as it's rotating around, these brushes rotate around to this side. And so the current is always flowing up the right side, up on the right, and down on the left. And that's how a motor works. So, and then that provides us our torque. They are now selling brushless. You can get I always try to get brushless vacuum cleaners or brushless drill bits or whatever. If you can do it and it's brushless, then that is even better. They use induction to get that current flowing through the loop. That's a better way to do it because you have less mechanical failure that way. But let's do an example because you guys are probably lost. Like, what? And so I'm going to write the equation. This is the equation that you need to know. The area of the loops times the number of the loops times the current times the B field. And then if you need to figure out the sine of the angle between them, between the normal and the B field, do that. That's in general, okay? But if you are asked to find the maximum, it's all the same stuff. You've got your number of loops times your area times your current times your B field. But the maximum is when the sine is equal to 1. So if the sine is equal to 1, this is your maximum torque. Torque max. All right, I'm leading into our example. And that's 22.5. We want to find the maximum. So what is the maximum torque on a motor with n equals 100 loops? The length is equal to 0.1 meters. The width is equal to 0.1 meters. The current, that is 15 amps, 15.0 amps, a lot of current. And the B field is huge. It's 2.0 Teslas. Wow. Okay, this is going to be huge. This is about what you would see on, you know what, I don't know. An electric motor in a car, I was going to say, but I don't know about that for sure. I think the length and the width are bigger on a car and the magnetic field is less on a car, and but I could be wrong. And the current probably is about the same, and I don't know about the number of loops. So I couldn't say. I don't know too many things. I don't know enough to say. But let's say this is a motor that has these situations. What is the torque max on that motor? So torque max is equal to our number of loops times our area times our I times our B. And that's going to give us 100 times 0.1 times 0.1 times 15 times 2. This is equal to 1. 15 times 2 is 30. So we have 30 meter newtons. Okay, I don't know if you guys remember, but in the end, torque is in meter newtons. And the reason I do torque as meter newtons, so that's the answer. I just want to do something real quick. Torque, meter newtons. Torque is RF, right? R times F, if the sine of theta between them is 90 degrees, good. So RF, which means the units are a meter times a newton, okay? However, when you look at energy, you have, let's say, work is equal to our force times our distance, right? So that also is newtons times a meter. And that happens to equal a joule. Well, guess what? This one, not energy. So I call this one a meter, quote unquote, meter newton, so that you don't mistake it for a newton meter. And which is equal to a joule. Okay, so meter newton, newton meter. Similar, very similar things, but torque is not energy. It's a measurement that is not energy. Okay. Now that we got that under our belt, so we've gotten torque out of one of these situations, and you can also get a meter out of them if you were to take your loops. So here's your bunch of loops going around, right? In and out. And then you attach a stick with a pointer on it, and you give it a scale. From like 0 to 10. And your scale runs like that. And let's say we've got in here, we've got a magnet. And here's the South Pole, and here's the North Pole. And it's an equivalent B field all the way across. Oh, whoops, I need to draw the B field with... Let's draw the B field like, oh boy. Okay. So there's our B field. then we don't have to switch the current on the loop, because if we look at it from the side, our loops are going to be like this over and over and over. Okay, now we're looking from it from the side. It's never going to, we're going to run in here, out there. There's no need for brushes or anything, because all we're doing is going back and forth in this way. We're going a little bit that way and a little bit that way. So the current never has to change directions in our loop, and that means we don't need brushes. So no brushes required. And this is a meter. Okay, and this is how you do a meter. A galvanometer is exactly this example. Exactly this. So that's what a meter does. So let's talk a little bit about applications. Applications of magnetism. One of the best applications applies to spectroscopy, mass spectrometry, spectroscopy. What is that? What is spectroscopy? So what spectroscopy does is it'll take some materials. Let's say you want to know the composition of some ink. We've got ink in our pens, right? So you get this ink and you want to make sure that none of it is toxic material. And so you want to break it down, you turn it into a gas. Why would gas have two S's? I don't know. So you have gas, and then, so here's your gas cloud, and then you ionize it. So you give all the molecules in the gas a positive charge, and then you make a B field. And you have your gas here. It's ionized. So here's your gas chamber. You let a little bit out at a time. This is where the ionization gets the ionized charged particles get their velocity from. So you put an EMF across here. So that gives them, the charge comes out here at V0 equals 0. And by the time it gets there, it has some velocity final. And then that velocity final, it comes out and does something like this. And we've already learned that that depends on the radius of that curvature. And this distance, of course, from here to here is distance d. D equals 2 times r. But at any rate, r is equal to our mass of the charged particle times the velocity divided by the charge of it and b. So if it's a positive ion, if it's a 1 plus, then that means its charge is 1.6 times 10 to the minus 19 coulombs. Okay, that's what 1 plus equals. Okay. So what that means is every single charged particle gets the same EMF, meaning they all have the same velocity coming out of this. But their masses are different, so when they end up in the B field, some of them might hit here, some of them might hit down here. And that's where mass spectroscopy comes in, spectronomy, whatever. That's where that comes in, depending on where your particles hit. They do a different, they have a different mass. So you can say, oh, well, a certain mass molecule or atom has a certain radius. So that's one example. This is what they did in when we produced all of our when we were making the bombs. Okay, we make bombs that are enriched uranium, or we want to make enriched uranium for a fission plant or who knows what. So we want to enrich uranium, and enriched uranium is 235, and regular uranium is 238. That's the most abundant source. That's the most abundant uranium. So we want to take 238s and separate out the 235s because we'll have a mix. 99% of it is this, and 1% of it is this. So we've got this bit, but in order to enrich this amount and make it more, we want to separate this. We're separating the cream from the whey, right? You take the skim the cream off the top. Well, that's exactly what we're going to do. And since the radius is proportional to the mass, this guy is less mass by 3 protons. This one is more mass. So more massive, more radius. Okay, so if we draw our circle and we do another circle, here's where the 238 comes out, and here's where the 235 comes out. And then we just collect it in these bins. So there's this distance here that is a no uranium land, and our magnetic field, of course, over here, making sure that it's all equal and uniform. And then here we are supplying a velocity to, what is it? Uranium chloride is the gas. uranium chloride ion solution. Okay, so that's one example. We still have the cathode ray tube example from way back. And then we also have, so CRT, cathode ray tube, or old television, also known as old TV. And then we have MRI. Okay, so let me just talk to you a little bit about MRI. First of all, it's really nuclear magnetic resonance. But here's the thing. The nuclear magnetic resonance doesn't jive with people. Nobody wants nuclears in them. And believe it or not, you have billions and billions of nuclears inside you. So they changed it to MRI, which is magnetic resonance imaging. Okay, so NMR produces detailed images, okay, using, you definitely need computers. Okay, so all of the scans come back with how do we want to say this? Different elements. So using the computers, we take the data from a scan that measures all the resonances and non-resonances, the good and the bad resonances, high and low, and it converts them into images. It would be doable by hand if you had 1,000,000 years, but a computer can do it in no time. So that's why we need the computers to handle those types of things. So NMR isn't perfect, all right? Everybody thinks, oh, I want to get an MRI right away, and it is not perfect. Sometimes it works really well, okay, for certain organs and whatnot. However, X-rays are better for broken bones because the NMR just doesn't see it. And breast tissue for when you're looking for breast cancers. Looking for cancer. The tissues are too similar. So when it's too indistinct, then not distinct enough, then you have to have an X-ray. So that's why women, when they get older, they have X-ray. They have to do X-rays all the time for their breasts. Yeah, some men have to do that too. So, all right. So, let's see. How are we doing on time? We've got 10 minutes. All right. All we've done is get through chapter 22, and we really need to do chapter 23, and I'm not going to do it now. Next, I'm not fast enough, I guess. So next will be another lecture starting chapter 23. And we're going to go chapter 23 through 23:1 through section 23:3. Okay, got to do that next. Sorry. Thank you for watching. Come on now. Come on now.